Hello students, let us recall some important points related to capacitors and dielectrics. Let us see how a capacitor works first. If it is connected to a battery of EMF V, a charge develops on the inner plates of the capacitors. So that charge here is Q. Now between the plates of the capacitor, we observe electric field, and the electric field strength can be given by sigma by epsilon naught, where sigma is the charge density, Q by A, where A is area of plates. So the electric field is given by Q by A epsilon naught, and by the definition of capacitance it is Q by V, charge per unit potential difference. If you calculate it, you will find it to be epsilon naught A by D. This is the case for parallel plate capacitors. The capacitance is given by epsilon naught A by D. Now what happens when we place a dielectric in the capacitor? Let's see that. So before that, we need to make one important assumption here. Let us remove the battery first and then use the dielectric. So note this point here, it's very important. The battery is first removed and then the dielectric is placed. Now what happens when you place the dielectric in the capacitor? When it is filled with a dielectric material. So dielectric materials, they get polarized due to the field present between the plates of the capacitor. Due to the electric field that is present between the charges here, the molecules within the dielectric, they get polarized, and this results in surface charges appearing on the dielectric on either sides. So if this is positive side for the capacitor plate, a negative surface charge develops on the dielectric, and this is the negative plate of the capacitor, and here the positive charge appears on the surface. Because of these charges, now there is another field present here. So as a result of this, the field within the capacitor gets affected. Now what happens when you place the dielectric like this? When it is completely filled with a dielectric material, then we say that the field strength usually drops, let's say by K times. Now where K is called dielectric constant. So the field strength is now E by K. It drops by some factor K. That is called dielectric constant. Now if you want to calculate the surface charge densities and why this happened, we can do that by calculating the net field. Here I am calculating the net field. This is Q by A epsilon naught, the field produced due to the original charges on the capacitor, minus the field due to the surface charges. Why minus? Because it is in the opposite direction. The field is plus to minus for the charge Q towards right, and the field due to the new surface charge that developed is towards left. Plus to minus towards left. So the net field is this minus this. Now by definition we say that it has dropped by K times. The original field has dropped by K times. So the original field Q by A epsilon naught by K. Now this will give you the surface charge value. This is also an important result. You should remember this. It is original charge into 1 minus 1 by K. Now let's see what happens to the capacitance. So the capacitance is given by Q per unit potential difference. Now because the field is affected here, the potential difference is also affected. The new potential difference is given by E dash into D, the new field into the distance. So we get the capacitance K times the original value. So that means the capacitance has improved. So the capacitance increases by K times when you fill the dielectric inside the capacitor. So these are important points, you have to remember this. So let us see what happens to different physical quantities when dielectrics are used. In first case, the battery is removed and then the dielectric is introduced. So there are three steps here. In the step 1, you charge the capacitor with the battery of EMF V. So the charge that develops on it is Q, that is given by CV. In step 2, we remove the battery. Now the charge on the capacitor still remains the same. It does not change. It cannot go anywhere because the circuit is open now. So the charge remains there and the field present there will be of same value. It does not change. The charge does not change and the field does not change. Now you have placed a dielectric inside the capacitor. Between the capacitor plates, we fill the space with the dielectric material completely. Now what happens to capacitance? Let's take a look at capacitance. We have already seen this. The capacitance improves by K times, where K is the dielectric constant of the dielectric used. What happens to charge? Because the circuit is open, the charge cannot go anywhere. So the charge remains same. And by definition, what happens to electric field? We have already defined it. The electric field reduces by K times. So the new electric field present will be E by K. And what will be the new potential drop? Because the battery is removed, now the potential drop across the capacitor plates might change depending on the field that is present. Because the field is changing here, the potential drop also changes. And V is given by E into D, but the new field is E by K. So it is into D, that means the potential also drops by K times. Because the field drops by K times. Now what happens to stored energy? It is given by Q square by 2C. The Q remains unchanged, but the C is improved by K times. So it is Q square by 2K into C. So that means the new energy is U by K. It is reducing by K times. Now what happens if you keep the battery connected and then use the dielectric? That is our case 2. The dielectric is placed when battery is still connected. Now whenever the battery is still connected, the battery does one thing, it maintains the potential drop across the points where it is connected. So it is connected to these 2 points, it will make sure that the potential drop is maintained to the value V, which is the EMF of the battery. That is the main idea. So the potential drop here does not change. But the capacitance is always improving by K times. So you can write it Kc. But the potential drop does not change here because the battery is connected. And the electric field also remains same. If the potential drop remains same, E is given by V by D, the distance is the same thing. So the field is also the same value, equal to the original value which was present. And charge. What happens to charge? Charge is given by C into V. So the new charge will be the new capacitance into the potential drop. New capacitance is K times C. So this becomes K times. The charge, new charge is equal to K times the previous charge. That means there is some extra charge flowing into the capacitor now. What is the stored energy now? It can be given by half CV square. We see that the potential remains unchanged, but the capacitance improves. So this is half Kc into V square. That means it is improved by K times. New potential energy stored, the stored energy in the capacitor is K times the previous value. So few things you need to remember are here. The capacitance always improves by K times. When you fill it completely with the dielectric, it always improves by K times. So C becomes Kc. And you have to check whether the charge is changing or not. If the battery is not connected, the charge remains the same because the charge cannot flow anywhere. The circuit will be open. But if the battery is connected, there is path for the charges to flow. And the battery maintains the potential difference across the capacitor as the same value. So it sends extra charge to the capacitor plates. And that becomes K times the previous value. Let us recall calculating effective capacitance when multiple slabs are used. So there are two cases, there are two ways how you can place the dielectric slabs. One, parallel to the plates of capacitor. Identify the plates of capacitor always. That's the first step. Here the capacitor plates are these vertical lines. These two short lines indicate that they connect the capacitor to the circuit. So these two are the plates of the capacitor. Now the slabs are placed parallel to the plates of the capacitor, and the slabs, their thickness is different. Let's say the slab one is of thickness T1, second one T2 and third one T3. They have the same height and area is same as the plate of the capacitor. So identify this, area is the same here. Now how do you calculate capacitance here? We split this system into 3 capacitors which are placed in series, and we calculate the capacitance of each capacitor, and we can use the series equation. The capacitance increases by K times. So here if the dielectric constant is K1, you can write the capacitance of this capacitor as K into its previous capacitance value. So that is K times K1 times epsilon naught A by D, but D is T1 here, the thickness. Similarly here it is K2 epsilon naught A by T2, and similarly the third one. So use the equation and we get C equivalent as this. This result is very important, you may keep a note of it. What happens when they are placed perpendicular to the plates of the capacitor? Identify the plates here. These two vertical lines are the plates. So now they are of different heights. The slabs are placed perpendicular to the plates of the capacitor. Plates of capacitors are vertical, the slabs are placed horizontal, they are perpendicular. So now they have the same thickness D, but they have different heights. Some portion at the top is now filled with the dielectric 1. Let's say it's filled up to a height H1. Similarly the second one H2, the third one H3. And the width of the capacitor plate is W. Now the area will be different in different cases here. So what do we do now? We split it into 3 capacitors which are placed in parallel. Now the effective capacitance is given by C1. For C1 it is K into epsilon naught A by D. So that is K1 into epsilon naught A by D. But area is different here. Here you can write area as length into the height, W into H1. Similarly for the capacitor 2, D is same thing, but the area changes, it is W into H2. So K2 into epsilon naught A by D. A is W into H2. Similarly for the third one. And the C equivalent here is C1 plus C2 plus C3 in parallel. So we get this equation. These two equations are very important. So keep these things in mind. Okay, let's see what happens if one of the slabs used is a metal slab. Out of these 3, let's replace one of the slabs with a metal slab. Now you know that in a metal the field drops to 0. So you can use this equation to calculate the effective capacitance by making use of the dielectric constant for metal, taking it as infinity, because it is very large. We know that when you place a dielectric, the field drops by K, but in the case of a metal, the field is dropped to 0. There is no field present. That means we can treat the system like having a very large dielectric constant value. So that is why you can use K, a very large value close to infinity, and you can substitute in the equation. So if here the slab 2 is replaced, what will be the final equation? Epsilon naught A by, for K2 we will substitute infinity and this term becomes 0. So the final capacitance will be epsilon naught A by T1 by K1 plus T3 by K3. You may notice that the capacitance now has improved, because you see the denominator, there is a term missing in the denominator, denominator decreases. That means overall value is increasing, the capacitance is improved.